So I am George Boitano. I run Simplicity Inc. We've been for a while now Elastic Managed Services Partners specializing in security. What we're presenting today is not a product, but rather just a method that we've used at clients to leverage the MaxMind database to enrich events within Logstash. So this is more of a cookbook. And we hope you find it useful. I'm going to present at the beginning, and then Murali is going to present the middle slides because he's the smart guy here. So, but first you have to deal with me here for a few seconds. All righty. So there we go. Here, let's talk a little bit about the background for those of you who may need a little bit of an introduction to MaxMind. So MaxMind is actually an interesting company. It's been around for a while. And what they do is they aggregate information on connecting IP addresses to latitude and longitude and other geolocation information. So if you've ever seen an application that tells you where an IP address is coming from, probably MaxMind is behind it. They do a lot of work. They're incorporated by a lot of different products to determine, but everything they do is based on you have an IP address and it tells you where that IP address is as far as it can tell. Its top application is for external IP addresses, of course, that are out there in the world. And it is used by Logstash and by Elastic to enrich incoming events of all different types with geographical information, which they call GeoIP. And the concept is very simple. If we look at our diagram here, we have a raw log record coming in that has a number of IP address fields. It comes into Logstash. Logstash, for event enrichment, it implements a concept called filters. It has a GeoIP filter that comes delivered with it that uses a MaxMind database that also comes delivered really with it by default. And that will add a field to the raw log record or to the document at this stage. It'll add fields about where that IP address is. So you can see after it's been enriched, when we ingest into Elastic, the destination IP will have some GeoIP data, the latitude, the longitude, the city, whatever they happen to know about that particular range of IP addresses. Now this MaxMind DB down here, we'll talk about that in a second. That is the database that the GeoIP filter uses. It's a very interesting database, and we'll be talking about it a lot. It comes in a freeware version, which is what comes with Elastic, with Logstash, and it's what most people use, called the GeoIP Lite. The GeoLite 2 database. They also will sell subscriptions if you want that contain more different kinds of information. We'll be diving into that here soon. So let's talk about our use case then. What happens is our clients come to us and they say, hey, it's great that for the external IP addresses, that is the IP addresses outside of our company, it's terrific. I can tell, where they're from. This one's from India, this one's from this one's from Arkansas, whatever. But I'm also interested, because I'm an enterprise, I'm also really interested in internal network information. I have all this information on my network, my subnets, in descriptions for individual servers. I have network segments even that I've isolated stuff with. I also have a whole bunch of different sites. I might have 20 server farms scattered around the world. I want to know when a raw log record comes through, I want to know internally where it's from. It's not really obvious based on the IP address. I mean, unless you've really spent a long time looking at those things, it's really hard to know which network it's coming from. So I would like to enrich them the same way we enrich the IP addresses from outside the company. And why would anyone want to do this? Well, the top use case probably has to do because where log record is generated in your organization has a lot to do with what it's from and how sensitive it is. So some assets are much more sensitive than others, like a point of sale device. If it starts complaining about malware infections, that's sort of a serious thing, and you might want to prioritize that. We're also, a lot of use cases we're building out involve compliance. And with any kind of compliance use case, HIPAA, PCI, whatever, you need to know whether or not the particular device that's creating the log records is within scope. So it'd be really nice to say, look, everything in this network segment is from PCI. And a lot of enterprises, they do segregate their network segments by the compliance use case. So we could flag that whole network segment. Everything coming out of here is in scope for PCI. We need to treat these log records a little bit differently. Once again, just more generally, it's really nice to know where these events are coming from within your company, which country, which state, which site, which store, whatever. This allows you to track malicious activity. If you start seeing the same sort of beaconing or malware or malicious activity log records you could track where they come across states. You can see the lateral movement and the infections. In general, though, if you're running a security operations center or you have an MSSP or you are an MSSP, knowing where the log records are from within the internal network can really help out with all your security analyst tasks and incident response. So then the next question is, why enrich events on the way in? And that's the last line in this slide. And that's an important concept, and is a huge concept behind Elastic, right? So Elastic is a denormalized database. And what that means is that, we're all used to relational databases with a lot of foreign keys. And, a particular record might have 20 foreign keys in it. And you look everything up, that works fine in terms of conserving space. But you have trouble scaling at huge volumes. The beauty of Elastic is that they store the data on the record itself, on the log record itself, and that's what allows it to do its magic and to be so fast and scalable. So what we want to do, if we know something about an IP address and we're using Elastic as our back end, we want to make sure that we put that right in the log record as we're ingesting it, rather than storing it somewhere else and then trying to cross-reference it later on. That's going to allow us to do all kinds of exciting, denormalization. It's going to allow us to do all kinds of exciting searches and analytics. And it's going to give us the really fast search and performance that is the hallmark of Elastic. So our data is denormalized. We want to enrich it on the way in. We want to do our work when we're ingesting it. And then once it's there, there's all kinds of exciting stuff we can do with it. So that's our functionality. What I wanted to talk here, the next challenge is our volume. So the real challenge here is that, in this particular implementation we're highlighting, we have 11 Logstash servers running 60 Logstash instances. We're using Kafka, which is great. We're feeding 4 large production clusters from 4 Kafka topics. We do about 150,000 events per second, all day and all night. We store about 1 petabyte. On a good day, Logstash can be, part of our job is to keep Logstash running. And at this kind of volumes, that's a job and you need to keep on top of it. So obviously there's a cost when you start adding these filters. And so what might work for a low ingestion place, you have to be a little bit more careful in terms of your strategies for a large ingestion. And this is what made this project interesting for us, because there's a lot of ways to enrich events with Logstash filters. We had to go find the best way to do it. Because we were, our Logstash instances are under a lot of pressure because there's spikes and things like that happening too. So we don't want to slow down the ingestion of Logstash and the ingestion into the Elastic database. We don't want Logstash to be a bottleneck. So the solution we're going to talk about today was born out of that challenge. That this is high volume, and hopefully it'll be applicable to what you're up to. So with that, I'll turn this over to Murali, but I will keep sharing and turning the page for him when he asks me.
Awesome. Hi, guys. So we started looking at different ways of enriching the data, we started with memcache. Memcache, you can basically come up with a solution to repopulate the memcache on a server reboot or when a service restarts. But then the main use case that we are looking at was to get the lowest or the smallest possible subnet for a given IP, and memcache doesn't solve that problem. The same thing with we looked at CIDR filter that's part of Logstash. It uh, it will scan your CSV file or whatever dictionary path you have, but then again, it will just return an attribute, whether it's true or false, but it will not return the attributes associated with an IP. So that probably does not solve our use case or the problem that we are trying to solve. The same case with the HTTP filter and Elastic. Yes, you can look up for an IP, but then it will not give us the lowest, smallest possible attribute for a given IP, but then it will also not scale to what we are looking for. And the translate it scales, but then it doesn't give you the smallest possible network. So none of this, we went through different ways of solving. These were some of the ways we tried, and we didn't get the solution that we wanted. So that's where Max Mind comes in our next slides. So George, please, next slide. So we started, we went to our Google knowledge base to search for information. That's when we found a blog that was part of Max Mind, says how you can write custom Max Mind database using Perl. So we started looking at it, and then we know with Logstash using Max Mind database, free or the light version of the databases, it can scale, and it stores the data in binary format, so searches will be faster. So, and we also know that it stores the data in IP, it's indexed in IP address format. So that basically what we want, what our problem was. So basically it's not a problem in our use case. So Logstash with custom database, MaxMind database, indexed in an IP address for field will give us what we want. And we also know that it will give us the smallest possible network out of the database. So any questions, please feel free to ask in our group chat, in the chat window. Okay, George, next one.
Thanks. And I would add that we were already doing GeoIP for external IP addresses on this on our current workload. So
Right.
we knew this solution was going to work because it already worked for the current GeoIP information from external IP addresses.
Right.
So we probably should have started with
it. Right. And also it supports the EPS that we are currently ingesting, like 150,000 events per second with the current Logstash instances. So it does scale very well. Okay. So you guys know the Logstash comes with some free, the light versions of the databases. The city is the default database, and you can also change the database type to ASN to get the ASN information, like the autonomous system organization and their number, and you can enrich it as part of your event flow. When in your filter section, you can do that. And you guys also know that GeoIP supports the Logstash. I guess it supports the commercial databases like city, country, ISP. And I believe now they're supporting anonymous databases and other databases also. And I believe that's there included in that link that we have posted there, included there. And you can also configure the cache size, and you can define your source fields and what your target field is going to be, where you want the data to be populated. And it's all done behind the scenes. The Java program or Java code that's there that maps your all the enriched fields to the relevant fields that you're defined in your Logstash filter. And we have also included the link to the filter GeoIP GitHub location where you have all the source code. Since it's open source, you can look at how the filter works, all those things. And as it says, it's written in Ruby. It uses GeoIP filter.java to read the database, and once the record is found, it maps the data that exists in the database into relevant Logstash fields that you defined in your mapping. And there is also a blob that talks about the MaxMind database itself, what it is and what format it supports and all those things. Yep. You can go to the next slide. So we started looking at the blog, the link that we have posted there. So we started looking at that. We created a simple one-line database first, and we were able to create the database, and we were able to search the database for that specific information. Once we know that we are able to do it, then that's when we started creating. I guess I have to go back and say one more thing here. Before we created our own database structure for this, defined our own database structure, we went with storing our data into the GeoIP GeoLight city database structure, using that structure and storing our values into the database. It worked. Then we had to make changes to the code. Once the data is populated in those fields, we have to remap those fields and remove those fields from the Logstash configuration. So that's kind of additional work that we had to do once the data is extracted from the GeoIP city structure like database. So that's when we thought we should create our own database. We'll have a control of what fields it has. And we can also write our own script or Ruby code to extract the data from the database and populate to the field that we want. So there is a little bit of extra coding, but it's we can call an external script to get the data out. So here's the simple definition that we defined. We define the database type, which is the network, and the description is self-explanatory. And in our use case, it was just IPv4 network or IPv4 address we want to store or we want to enrich the data with. So that's why we defined the version 4. And also we had to make sure that it has to save the private network information. That's why we had to define that parameter, which is highlighted in that screen in this slide. Remove reserved networks equals 0. So we didn't realize that in the initial phase. We went with 1, and then this data was stored, but the data was stored, but then we were not able to retrieve that information from the database. So we did some more Google search, and we found that we had to do set that private network to 0 so that it can save it, and we can also search for that information. Okay, next.
And I would just add to that, really, that the IP version the MaxMind binary tree structure and the way that the database works is fully compatible with IPv4 or IPv6.
IPv6,
so
right.
It's not a limitation. It just so happened that the internal network we were dealing with was all IPv4, so that's what we specified here. But it's fully compatible with both. And if we were to specify 6, it would be compatible with both 4 and 6.
Right.
Okay.
And so we had to pull the data from pull the data and store it in a tab delimited format. And here is a simple Perl script that basically does a regex matching of the line that's saved in that input file, and maps the regex values extracted into relevant fields like the name, network subnet, site, and network name. So if you have additional fields, you just have to make sure that the regex matches your log line, and then you can extract those and then define the network tree similar to what the tree insert network statement is on the next line. And this is how we created our network database, network or custom MMDB database for our search purposes, for our use case.
Nice and easy.
Right. So here is a sample of the input file, and once it goes through the Logstash, so that's how we see it in Elastic. So those values that you see for the description, source description, those are all part of the CSV file. Not CSV file, the input file. For some reason, I'm always thinking a CSV file. It's not a CSV file. Okay.
And I would also add, since I put this data together, we were originally going to redact our client data, but it was just too much. So this is completely imaginary, all this data. And I apologize if I got some of my side of my subnets don't match my IP addresses if I get anything wrong here. But this is what it looks like in Logstash, and this is what the input file that we build the MaxMind database looks like here on. That's the first thing here. It's tab delimited, but it could just as easily be CSV or whatever format. You just pull it apart with the regex.
And if I'm going very fast, please let me know. I will slow down. Okay. And so this is one of the visualization we created that gives us what the source network zone and where the target network, what's the traffic flow between internal traffic flow is from the enriched data that we have in Elastic. So I think the visualization is basically a Sankey visualization that's on, if you do a Google search on Sankey visualization using Vega, this will show up. I basically took that example and they changed some of the fields that's part of the sample and created a visualization to see what the traffic flow looks like between a source and a destination zone. And this is just an internal network only. It's not anything to do with external at this point. Yep, I'm good. Next slide.
Okay,
I think it's up
I'll
to for you now.
apologize for this, yeah. And I'll apologize for this hokey text that I typed in here. I took something that was real, but I put my own stuff in on top of it. So it looks nicer than this in terms of the actual text.
I guess if you go back one slide, George, I would like to say something there. So the one thing you can, if you're looking in Kibana, and if you move your mouse over those lines, it will give you the total event that's between those two, between the source and the destination, and it will also give you a percentage of what the total percentage of the total traffic is. And it looks nice in Kibana. It looks nice. The screen looks nice here too in the presentation test in the slide as well. Okay,
Thanks.
I'm good.
Okay. Well, thanks, Murali.
No, thank you.
I'll talk here. I know that there was some interest in threat intelligence enrichment. That is our next use case that we're working on implementing right now. And if anyone's working on that, please contact us directly. We'd love to talk about it with you. So the point here is that now that we can take an IP address and associate with any kind of arbitrary data we want, why not use it for some other purposes? So the most obvious use case is threat intelligence. There's a whole bunch of threat intelligence feeds out there today. I mean, it's really turned into a big business. And a lot of them, I would say most of them still, are keyed by the IP address or maybe a subnet. We can load these into our MaxMind database and then enrich them with that information. There's a whole bunch of threat intelligence feeds. MISP is really popular. Threatfeeds.io, these are curated from a whole bunch of other sources. They're pretty, normalized into a standard format. They're really easy to use and really easy to set up. A lot of enterprises belong to industry consortiums that share threats, like the Open Threat Exchange. That stuff usually shows up as CSVs or, sticks taxi format. Either way, easy enough to turn it into a flat file and read it with a regex and put it into MaxMind. There's paid curated proprietary feeds like normally ThreatStream being a very popular one. But the best kind of threat feeds are the ones that you generate internally. I've seen activity from this site. I've seen surveillance activity from this subnet that's attacking me specifically. I'm seeing, beaconing to these particular sites, and I know they're bad, or something like that. So the best way to, the best use case is to take your own threat intelligence, the IPs that you've determined are no good, that are malicious, and then turn those into a CSV or a flat file and load those into MaxMind. And then we can write content in Elastic to really make those events, when we see communication that involves those IPs pop out at you. And, we know it's a problem because we've seen that problem here at our own enterprise. So we think that this is a, very straightforward use case. We'll just take whatever threat feed we have, we'll turn it into a flat file, we'll read it with a regex, we'll put it into MaxMind, we'll write the filter. It's easy as can be. And we will include information. A lot of these threat feeds have lots of nice information on them, like the certainty that this is a malicious event, or there's a malicious IP, what kind it is it click fraud, is it beaconing, is it spam, whatever. All kinds of information there so you can prioritize stuff. And you could prioritize them in your Elastic query DSL searches, so that you could create a search to say, give me the worst things that are happening on my on my network right now, and it could certainly do that. We have that capability in the query DSL to prioritize search results, so it's a natural fit. So let's go on to some other applications. I mean, why should we stop at threat intelligence, right? It's really nice to know if you're working in a security operations center, you're analyzing security events. It's really nice to know if you see a suspicious log record or suspicious event. It's really nice to know what vulnerabilities have been detected for that event. If we see suspicious logons and then we see like that Red Seal has told us that this Linux server is using all default passwords, that's valuable information. And if you can store that on the event itself, that takes like something that might take a while to research and turns it into like a 5-second operation. And for that, as I said, if you can do that for your SOC manager or your MSSP, they should take you out to lunch like every week, because that's really saves them a lot of time. Another thing that's super useful is the machine state, right? Like a lot of times, McAfee say it cleaned up a virus infection on this particular endpoint, but it's still doing bad things like the next week or the next day. It's extremely useful to be able to store that information in, and we would like to put it into a MaxMind DB of the, the machine state. We've seen an incident on this machine in the last 30 days. We've seen suspicious behavior on this machine in the last 2 weeks, all kinds of stuff. If we create a MaxMind DB with that, then we can enrich that with that information and include that machine state in the actual events. That would make your CISO quite happy, because it would save him a lot of money for people like doing historical searches when they see an event. And an security analyst often has to go back in time on a particular device and see what's happened. If I can give him a quick summary, then that saves that person a lot of time. Another, a little bit more far out application of this, but not out of the realm of possibility, is identity attribution. We could create a MaxMind DB that logs when a user logs on or off, that contains that information. We know when a user is signed on if we're getting the information through Logstash or into Elastic. We can create a entry dynamically in the MaxMind DB for that, and then we can attribute activity on that device to that user. The biggest problem with user and behavioral analytics in general, and insider threat is, I guess, what it used to be called back in the old days, like 5 years ago, is that not every log record contains a user ID. A lot of log records, they don't have user IDs on them. So you see a suspicious piece of behavior like some pinging or some lateral movement, things like that, but it doesn't have any kind of user ID, so you don't know which account has been compromised. But if we can see the original logon to that Linux box, say, then now we know we can store that information, we can store that state, and if we see that logon and then we see malicious activity, we can tie the two things together and we know which account has been compromised. And for that, someone should buy you a new car if you can do that, because that saves like the security incident response team all kinds of time. And it also, it makes identity attribution really useful, and it makes, if you're implementing, user entity behavioral analytics type applications on top of Elastic, which is a super interesting topic, that's very useful as well. And it will empower those things. All right, so I think, in the interests of clarity, we'll talk, or honesty, we'll talk a little bit about the limitations of what we've done here. We've implemented this for 70K of EPS. It's eventually going to be all 150K. We have our custom MaxMind DB is not small, but it's at 8 megabytes. It's not large either, though. The MaxMind DB works with binary tree searches. So if you're going to which is because of that, like all binary trees, they can get unbalanced if you're doing a lot of I/O on them. It's not a problem with this. The internal network is rather static. And the beauty of these binary, but if you have a really dynamic application, you'd have to take that into account. But the beauty of binary trees is that the operational complexity, in general, average grows according to the log of the number of entries, which is, as good as you're going to do. So this thing could scale up to have a great deal of entries in it, I think, and it would still work pretty well. The other limitation, which we've mentioned before, is that the IP address is the only key that will work. So this isn't going to work for host name or text-based data, user ID. For stuff like that, we'll need a different filter. That means that a lot of threat intelligence, maybe half of it is based on host name or URL or a file hash or another kind of IOC, indicator of compromise. That's not going to work for the MaxMind DB. We're going to need another filter for that, but that'll be the next presentation. Okay, we'll finish with this. You know, we are consultants. We specialize in enterprise implementations of Elastic for security, all up and down this pyramid that we've created here. So our focus on this presentation was parsing and enrichment. But if you have a use case around Elastic for security, we're SIEM people from way back, and we've been really Elastic bigots here for the last few years, and you know, that's what we do, and we'd love to talk about stuff with you and see if we can help out. All right, that will do it. Now I promised I'd be responding to chats, but I haven't, so should we stop the share and just see what's going on in the chats, or let me just see if I can, let me take a look at the
I think Bradley's gotten back to all the questions so far.
Oh, good. Let me go. So there's our Q&A feature. If anyone wants to, is that where we're putting questions in, or?
Yeah, I think all of our questions that I've seen have been answered. But if folks do have any more questions, there's still a little bit of time.
Let me go take a quick
Bill, I see that you would like a copy of the presentation. We will get to you one. And for everybody else, the recording will be posted to the event page. And we can upload the slides there as well. But Bill, you will get the presentation.
Yeah. It looks like Kevin's got a question here on regarding the vendor side. Do you just host, or will you maintain on-prem in the customer tenant? Well, we are consultants, so we'll do whatever you want. If you want us to help implement, I think it would certainly work either way. I mean, wherever Logstash is running, this can run. We most of our managed service implementations tend to be on-prem, but it will certainly work in Azure. We've seen it work there. So.